machine is not working. Okay? This is why we go analog here. So whenever we saw last time the SQN, okay, let me make a larger review. So we said that whenever we have IIDs, okay, but the IID samples are equal probable, we go for fixed encoding. Whenever they are non-equal probable, we go for the variable Huffman code, right?
Yes.
Then we have the other case whenever they are non-IIDs, okay? So the samples depend on the previous one and so on. Okay, what to do? Whenever they are equal probable,
PCM.
we saw the PCM. Whenever they are non-equal probable, we will see PCM plus something, okay? We will see it today, inshallah, okay? Plus, we will see other options here, okay? We will see two more options whenever I can put them now, something called delta M and differential PCM. Whenever we will reach each one of them, I will motivate, okay? Why we need these other options. Good? So, yes?
Delta M and the differential, they are for the non-proper or they just...
I said I will explain them whenever I will reach them, okay, with their motivation. Good. But now it's good if you want them to have in the table. Good. So here, SQNR. Last time we obtained an equation for the PCM, SQNR, and we saw that it depends on B, the number of required bits. It depends on the range, X max, I think it was named, right? And it depends on the signal power. Right? And we said that always, obviously, it is a signal to noise, so we want it to be the largest possible. Good? So how to make it larger? We have these three parameters to make it larger. Okay? Right? This is what we stopped last time.
Yes.
Right? So what to do? So with the B, yeah, obviously, whenever we increase the number of bits, consumed bits, what we will do? We will achieve more resolution. Okay? So here, more resolution, especially if it's video, which means more quality, right? But we know that increasing the B, okay, is not for free, like everything in engineering, alhamdulillah. What is the drawback?
Cost.
That's it. So here, we will increase, the bad stuff is that also we will increase the required data rate or cost. Good. But you as an engineer, you are the ones who should be aware of all the parameters. And it's like a game, okay? You have to increase this, you have to increase that, you have to check what is your application. It allows you to increase the required cost or not, or you have a strict restriction on the cost, so that you know what to change. Good? With the X max, here, X max was in the denominator, I think, right? Okay, so whenever we increase X max, our SQNR will decrease. And we put a similar idea, last time I think I explained about DFT and these. So whenever we have voice signal, for example, it's from 100 to 20,000, okay, as a bandwidth, and this is the signal, right? So they decided that to cut the signal and to make it at 4,000 or 3,500, depending on the standard. Because why they did that? They decreased the range, okay? By decreasing the range, okay, it becomes more suitable, and they found that here, the amount of data that is here, and it's 5%, we can neglect. So decreasing the range it's like you concentrate whatever you have there. This is why here with the SQNR, the lower the X max, or the lower the range, you will have better performance. Also, whenever it is lower, if you have only 8, let's say, quantization levels, so here you can put them like this. If you have to put the 8 on all of them, then they will be far away, the steps. Clear? The last one, question so far? Sure? Abbas, lost? You said? Shahab? Good? No questions? Amir? Yes, please.
So how, like, I'm going to use a bandpass filter to make this thing.
Yes.
Okay.
Remember that we are in a digital world, okay? So whatever filter you have to apply has to be digital. So it's cool. MATLAB, C, Python, whatever. The last one is the signal power. Okay, and the signal power was in the numerator, if I properly remember. Okay, so increasing the signal power will increase the SQ&R. Well, if the SQ&R is the signal to the noise of the container, so the larger the signal, this one will be larger, obviously. Okay, but yeah, we can increase the signal power. But increasing the signal power is not for free. Here, increasing the signal power. This will increase the SQ&R. Here I should have added that increasing the X max will decrease the SQ&R. Good. Increasing the signal power will increase the SQ&R, but again here we have to be careful. Increasing the signal power, for example, if it is a mobile phone, it means that it will increase the amount of transmit power that will go from it. It's how to increase the signal power. Is this always good? Do you see any disadvantage whenever you increase the power of your mobile phone transmission? Yes, you have to recharge faster. So here, increasing the signal power, this is good, but also, هذا كان نقول good, this is bad. Okay, so increasing signal power, it's bad because you will consume more the battery if it is a handheld. So you will decrease the battery life. Battery life. What else? Whenever you transmit, so you can increase the power to whatever value you want. Do you see any disadvantage of increasing the power? Heat. So yeah. Well, also your mobile phone or laptop, you see that you will increase the heat, and this is also bad. Both of them, they are bad.
Like what?
Sorry. Cost. Linked to the battery life. Okay. Whenever you have to charge more, or if it is a tower of Ooredoo, they have to pay more to Kahrama, or whatever is a generator or router or whatever, the electricity bill will be larger for the company, factory, or whatever.
بس ايش معنى البي اللي فوق الاكس ماكس؟
B, and this was part of this SQ&R equation. This was the bits.
Next bit.
X max. That was the range.
Double B.
Now, increasing the number of bits will increase the resolution, will increase the quality. This is good. But also it will increase the required data rate or required cost. This is bad. شوي ماشي بطيء يا حمزة بالكتابة ليش؟ حلو الحكي. Okay, good. I will stop a couple of minutes so you can write down.
So there's disadvantage for decreasing X max in order to increase the SQ&R.
Definitely. There is the nice stuff in engineering is that always whenever you increase something, you will have advantage and disadvantage.
I think the level.
So whenever you decrease the X max, what will happen?
Level quantization will decrease.
The quantization levels width will decrease. This is good, but also
the error will be increased.
Which error?
For quantization.
No.
Bits will.
You will use more data. So here, instead of 100 to 4,000, if I do it to 2,000, then you will have more loss on the original data. This is bad. You want to add it? So here, whenever you decrease the X max, you will increase the SQ&R. It's written here, but this is good. But also, whenever you decrease the X max, you will decrease the considered data. So here you have a loss of that. This is bad. This is good. Again, this is what is wonderful about the engineering, electrical engineering especially, okay? There is no conclusion, okay? So always you have to check what is the scenario, what is the application, whatever you are doing, and based on that you will decide. You will Google it, okay, and you will find someone else who said that decreasing the X max is good. Or someone else saying it's bad. Or someone good, or bad, okay? They are all right, okay? You have only to check what they are doing. Same.
The concentrated data be decreasing, that's a good thing?
I will not answer to your question because you were not here. It's unfair to your colleagues. Yeah, consider data. So here, instead of all this, you are decreasing the amount, so you have more losses. Good so far? Can we move on? I want just to comment on one more disadvantage of increasing the signal power. Question to Khalid. Do you know how much is the amount of transmit power from your mobile phone? So let me give you this. So here, 1 watt, 0.1 watt, 10 watts, 100 watts, 1000 watts, none of the above. لا بالفاينل usually there are 10 options. Good. Khaled, which one do you think it is more suitable by sense?
None of the above.
غلط. Khaled.
0.1?
0.1 watts from the mobile phone? So let me ask, for sense-wise, how many, whatever you have at home, what do you have at home? How much is the TV consuming? How many watts?
100.
Something like 1,000.
No,
400.
400, 300, something like that. How much is the PlayStation consuming?
1,000.
300.
Same, okay, a bit more. 500, 550, something like that. Kettle at home.
That's less.
150.
How much?
50, 60.
50, 60 the kettle.
That's less, isn't it?
You don't, have you ever bought a kettle?
Yes.
And wherever you bought the kettle, okay, you went and you checked, they told you how many watts is it?
5.
Yeah, based on what you bought the kettle then?
So how it company?
Company?
The price.
So, okay, good. Company name, which one you bought?
Panasonic.
Panasonic, they don't make kettles.
Maybe they're stopping.
No, they never did. Okay, good. Guys, you study electrical engineering, right?
Yes.
Oh, they don't ask you about the stuff at house, at your home?
They asked
No.
how to change bulb.
What?
They asked how to change light bulb.
They change what? Change the bulb?
Yeah.
I'm sure you don't know how to do it, right? Good for you. Okay, good. So the kettle, okay, is usually 2,000 watts, 2,500 watts. This is, and wherever you will go and to buy, they will tell you, this has more watts, okay, so it will be faster. Good? Hopefully. Good? So, your mobile phone then, what is the range of the watts that it will consume? No?
12.
12. Why 12? ناخذ رابع لتر.
بتذكر شفتها مرة ورا.
خلاص. No one knows?
Mobile?
Yeah, your mobile phone, how much power does it transmit? You have you bought a mobile phone? Alhamdulillah. Good. It came with a small booklet. Have you read it?
No.
Alhamdulillah.
I know some chargers are like 40 watts, 20 watts.
Yeah.
So
Yeah, good. There are some chargers that are 20 watts. Okay, so they are usually written that to be fast charging.
Yes.
Because they will provide more watts so that it is charging more. Okay, but how much the phone transmits? The phone transmits 1 watt maximum. Usually, as your colleague said, 0.1, and hopefully it will be 0.001. Why? Why the mobile phone transmits that small amount of power?
it's more efficient.
Okay,
The radiation is lower.
that's it. So whenever you talk with your mobile phone, and this is a rule whenever they design phones, that they know that people usually talk like this. So, and this one, whenever it radiates all places. So whenever you do this, half of the power goes inside your brain. Half of the power, whenever it transmits, goes inside your brain, and that is useless. But not only useless power, what will happen to your brain? هو أكيد شكله دمج. Okay, good. Okay, so yeah, it could be harmful. So here, this is the issue. Whenever you increase the signal power, you have to be careful. You have to check the standard. But yeah, here you can increase health concerns. Good. So increasing the power, you have to check. Okay, if this is a transformer for kahrama, and whenever you increase the power, maybe it's not suitable, or maybe it's not allowed. Okay, so again, there is no magic answer. You are the one who have to decide. Good, يا حذيفة? Lost? Sure? Hisham.
What about the headphones? Are they also transmitting? Some are using the headphones. Like Bluetooth.
Bluetooth, okay, good. Fine. Bluetooth. Yeah, fast answer. Okay, so Bluetooth, notice that the Bluetooth, it's another transmitter. So this one also transmits from the Bluetooth to the mobile phone. So it's could be even worse. Okay, and for the wired one, okay, they have discovered that whenever the signal is transmitted from the mobile phone, this wire will behave as an antenna, so it will absorb and retransmit, but at a much less. Good so far? So this is about the SQNR. And again, so many parameters. What is the best combination? There is no best. Every scenario has a best. Okay? And you will be asked to obtain the best for whatever scenario. Cool? Clear? Good so far? Questions? No? Good. So this is the PCM blah blah blah. So PCM now, what was the next one? PCM
Compressor.
with the compressor. Good. Like I told you about the compressor. This is whenever it is non-IID, it is PCM, but also non-equal probable. So what is the idea of the PCM with the compressor? Well, first of all, can I?
Yes.
Non-equal probable, non-IID. Do you remember whenever we wanted to do quantization? So whenever we have a function and we wanted to quantize that function, we were doing this. Right? But then whenever it was non-uniformly distributed, what is the solution that we said that we can do for the quantization? Do you remember?
Solution for what?
So, okay, good. Let me repeat. The quantization, whenever we saw the quantization, okay, we said that there are two options for the quantization. Uniform and non-uniform. What was the difference between them? So that's why here, whenever it was uniform, let me make it two more here. 8 intervals that are equal in terms of their width. Good. On the other hand, if the samples are non-equal probable, what we can do? That's it. So here now we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah. This one is more. So here now we have the same amount of intervals, but they are not equally distributed. Okay? They are not same in terms of length. Good? So why we do that? Because maybe here the function was like this. Here very improbable and here very probable. So we compensated for the different probability by making non-uniform steps. Clear this idea? Do you remember it?
Yes.
The same approach will happen here. Okay, the same approach will happen here on the PCM with the compressor. What is the idea? Is that the PCM is doing very well, okay? And people in the industry, they really like it, the PCM. It's still implemented up to today, okay? PCM is still there, okay? So what is the idea with the compressor? The compressor said, okay, if we have a function that is not equal probable, okay, what we will do is that we will, so here we imagine that here we have the analog signal. The first thing, it is sampled, so here sampling. Okay, good. So before here quantizer, and then here we have the source encoder, right? This is what we have seen in the chain. Channel encoder, blah blah blah, whatever. Good? Do you remember? So and this one on the transmitter. Good job. I put it all together. And the receiver, so that I can change. At the receiver side, here the flow is like this. The flow comes like this. So here we have
Source decoder.
source decoder,
No reverse. For
no reverser for the quantizer. For the sampler, we have interpolator. Good, and then we can hear the analog signal or see it. Hi, how are you? Hi, how are you? Good. The quantizer will introduce some error, okay, but still the signal is audible, right? This is what we have seen, nothing new. Good. Then the PCM, they came and said, okay, we don't want quantizers or source encoder. PCM, and here at the receiver side it's called PCM receiver. Good. So again here the function because it's PCM, then here definitely this analog has to be non-IID. So they said, can we introduce something in the chain that we still use PCM, but these non-IID and non-equal probable, they become equal probable? How is that? They said, okay, if you have a function, imagine, let's make it easier, okay? So a function that is like this. Here, this is like the PDF, okay? So here the probability is 0.6. Let's do it like this. Imagine this function has 4 intervals. So here for the first one 0.6, for the second one 0.25, 0.1, 8, 9, and the last one 0.05. So this is like the PDF, the distribution. So in the first interval, there's a 60% of the sample to be here, 25% to be here, 10% here, 0.05, 5% to be here. Good? Then they said, obviously, this is a non-equal probable. They said, can we make it equal probable? How? They said, okay, what to do? We will multiply it by another function that will be like this. And this other function that we will multiply it will be, for example, how much we want to do it. So here 0.6, 10 over 0.6, 10 over 0.25, 10 over 0.1, or 10 over 0.05. Whenever we will multiply these two functions, what will happen? Okay, if I multiply this by this, okay, this is what we will look. What we have made that now all the intervals, they are equal probable. Good. This idea, okay, this is what we call a compressor. Compressor, or some people call it compounder. We will see now it is the same. Well, what does it mean, compress? To compress, it's large, we make it smaller. What the compounder, it is small, we make it larger. Write down then I will talk.
So we want to multiply by the reciprocal or?
Reciprocal, yeah.
Doctor, when now we introduce DCM, you can retrieve the signal back there? Because last time when we talked about it, we just said you can't, right? Because there's no quantization.
Still, because the quantization now is inside the PCM. So now here it is PCM receiver. The value whatever we have has been quantized. Okay, it is lost. But yeah, it's still a PCM receiver. So here, 100% recovery? No.
But better recovery.
But yeah, good recovery, excellent recovery, but not 100%. Khalid, phones are not allowed. يعني even to go outside to answer the phone is not allowed. You stick here. And as one of my colleagues said, دخول الحمام مش زي خروجه. You stick here. lecture?
It's already recorded.
Yeah, I do them. So please share it with your colleagues after that.
ان شاء الله. بس الظاهر قاعد تسجلوا كيف حيكون حجم الفيديو شوي كبير بزياده.
وبس سجلت الدوكي.
لاني تو استوعبت الموضوع.
يمكن مسجلها 2K 60 فريم.
لا اكيد 60 فريم مش احتمال.
وشرحنا على ال 4K وال 8K وال 8K والاخر سجلت 2K.
الان تذكرت الموضوع.
طيب ماشي اوكي. Sam, stay with us. Done, can we? So let me repeat. So here the samples, okay, they are non-IID and they are here non-equal probable. PCM will not work, guys. Okay, so whenever they are non-equal probable, the PCM will not work. But we want to use the PCM. So what to do? They said, okay, use here a unit. And this is the compressor. So that the compressor will transform, here the compressor, transform the non-equal probable into equal probable. Now the PCM will work. But we know that everything you do at the transmitter, you have to reverse it at the receiver. So you put here a compressor, here at the receiver. You have to put the reverse of the compressor, which is the compounder. You want to call this one to be compressor, and this one compounder, good. You want to call this one compounder, this compressor, good. Because again, I was saying that compressor means that if something is large, you want to make it smaller. Compounder, something that's small, you want to make it larger. Okay, so depending on what you are looking to. So here, this area, it has a large probability. With this compressor, you make it smaller. This area has a low probability. With this compressor, you make it larger. So other words, here this one has reshaped, okay, the samples into non-equal probable into equal probable. Clear? So this is the idea. And if you can reverse it at the receiver side, things will go perfect. Is it clear how this will work? So still our PCM is the normal PCM, has not changed, okay? But now with this pre-unit, okay, we fix the issue of the non-equal probable. Cool. You can ask any how the receiver will know what the transmitter did. Who is lost? Just a minute. Who is lost so far?
I don't get.
Tell me where you get lost.
I didn't get why we make them equal probable.
Okay, good point. Who else is lost? Khalid.
Not lost, but before the compounder, which one will be equal, then we convert it to non-equal, then about the PCM?
Okay, good. Who else got lost?
compressor or compounder.
Okay, good. Who else got lost?
The compressor block.
Hussein.
Yeah, the question you just asked.
Okay, good. So I will repeat. Okay, and if I miss one of your questions, let me know again. So, before, whenever the signal was here equal probable, okay, please stop writing so that you get the point, then I will give you time to write. Okay? So, whenever it was equal probable, so here before we said PCM for equal probable, non-IID, all of them that are non-IID, but whenever they were equal probable, so we use the PCM, and this unit was not there. Good? PCM needs the input to be equal probable. Non-IID, but has to be equal probable. Cool? Then whenever here we have the signal, it is non-equal probable. What to do? La hawla wa la quwwa. Okay? So this is how the input comes. So we need a way to change the info or to adapt the info so that the PCM still works. PCM needs the function to be equal probable. So here, the input to the PCM has to be equal probable, and the output of our sampling is non-equal probable. So here we put this unit to make our task. Okay, to convert non-equal probable to be equal probable. Good? Motivation clear? How to do it? We go and we check each probability. So here, whenever it is non-equal probable, so we have samples that have large probability, samples that have low probability. So what to do? We want them to be all equal. So we find what is the distribution here. This is exponential, Gaussian, whatever is the distribution, and we reverse it. Wherever here, we reverse it and we multiply. The answer will be 1. So here I put 10, so it is 10. I put 100, 100. I put 1, 1. Because, why? You see here, every value is reversed. Every value is reversed. You see?
Yes.
Good? And then here, what I will obtain? I will obtain that the probability now for this, so this, so this, so this, they are all equal. Clear? This operation of reversal, we call it compressor or compounder. It is the same word. So how is it the same word? This one means make it smaller, this one make it larger. Now, depending on what you want to make it larger and smaller, this part, you will make it smaller. You want to decrease this one so that it becomes this one. This part, you want to make it larger so that it will become equal to this one, right? So we are doing compression and compounding at the same time. Compression for some of them, compounding for others. Clear? This is why I said that this one or this one is the same, but yeah, this will be applied to some samples, this will be applied to other samples. Good? And if you want to call at the transmitter, you want to say, well, I use the compressor, then at the receiver, you have to be careful that you say, I am using the reversal for this one, which is a compounder. Here you want to call it compounder, here you have to call it compressor. Clear so far? Yes. Just a minute. So now we have motivated this one, okay, and we have seen what is the reversal for them. Now, is it difficult to find the reversal? We have to find the distribution. Once we find the distribution, okay, we find the reversal. It should be straightforward, okay? And in MATLAB, I don't remember if in C, but in MATLAB, it is a direct function, okay? Do a compressor, it will tell you the function, its compressor, output is equal to 1. Good so far? Questions? Khalid? بركة.
طيب دكتور بالنسبه انت قلت انه البي سي ام بس اكسبت الايكوال بروبابل.
يب.
بس احنا الحين لما نعمل ترانسميت
English please.
اول واحد when we transmit the first PCM the equal probable will change why we use the compounder. It will be none after we transmit.
So you are comparing to last lecture?
No,
today's lecture. So here the compressor, okay, will change definitely. Here you added a unit at the transmitter that changed. So here it was non-equal probable. My input was non-equal probable. So whenever you did the compression, you make it equal probable. Why? Not because we want, but because it's a must for the PCM to work.
Yeah,
at the receiver, whatever you say, hi, how are you? Okay, here you should hear, hi, how are you? If you don't do compression, okay, you will hear the words separated. So how are you, and so on. So you see it? So whenever we will have here the function, it will not be exactly as this one. We change its probabilities. So whenever you will hear it, you will not hear it properly. You will hear the same sounds, but not properly as they were sent. This way, we said that we change here the distribution, we refix it again here, so that the sample here is equal to the one here. So here, at the compressor, the PCM receiver, here they are equal probable. Here they are non-equal probable. This one is the reversal of this one. So if this one converted non-equal into equal, this will make equal to non-equal. Now the receiver will hear whatever has been sent, or will see whatever has been sent. This was your question?
Yes.
The other Khalid.
My question was here we use the compressor and the compounder together for the whole sample. But here we are using the compressor for like just part of the sample.
That's it. It is, whenever I say compressor, it is I am changing. So I said, you can call it compressor, compounder, but you will change the distribution to make it from non-equal probable to be equal probable. Good?
Doctor.
Hussein, why you keep talking? Don't ask him, ask me. What's your question?
No, I was just asking, it should be non-IID and equal probable, then it will be PCM because it would be IID and equal probability.
Whatever we are studying today, all the day, and last day, they were all the time non-IID. IID is fixed to Hoffman and so on. So we are all the time with non-IID, but be careful. Non-IID is not equal to non-equal probable. They are two different stuff.
Why do we need to make it equal probable?
PCM needs to be equal probable, otherwise it will not work.
For fixed encoding or?
For PCM. More stuff. Well, so who else? Hamza, clear? Sha. Amir, clear? Abdullah Muhammad, he's not here, right? Okay? I haven't seen him. Abdul Aziz.
No.
Abdullah Ayman. Abdullah Ahmad. مين أحمد الأشقر؟ Good. Questions so far? Sure. Good so far? Yes, please.
Why 10, doctor? We can put any number? Or?
Any number. I can put 10 just for an example. It could be 1. Usually, actually, it is 1, but I put 10 in. I don't know why I put 10. Good. Clear.
على ايه اساس بتحدد الرقم يعني عمليا؟ يعني هل هي 10 ولا 1 ولا 2؟
Usually it is 1. Because we don't want to change the value of the transmit power. If we get 10, you have to be aware later that you have increased here the value. Okay, at the output it should be 1, as I said before. Good. So last comment here that I asked and then I stopped. So if here we did this compression, how the receiver will know it? Because the receiver has to reverse it, right? How the receiver will know it?
It will be equal, so it will convert to non-equal.
But yeah, here, how that the receiver will know that the input signal was exponential and it has reversed? Because here the input signal could be any distribution. It could be like this, it could be like this, it could be like this, and distribution. How the receiver will know what the transmitter did?
PCM?
This is not PCM. Here, how the receiver will know what happened here?
You will tell him, doctor.
What?
You mentioned the thing, so maybe it's a differential one.
No.
Interpolating?
My interpolating is for this one. Here, I need. It's clear my question. Here, the transmitter changed the distribution, so the receiver should reverse it. How the receiver will know what the transmitter did?
By taking the input?
Sorry?
By taking the input?
No. The receiver does not know them.
The compressor rate will be set also.
That's it. So here, the only way is that the transmitter should communicate to the receiver that actually it is a table. Okay, so old phones, they have a table of 16. So 1, 2, 3, so distributions and numbers. So from 1 to 16. So the receiver, the transmitter will say to the receiver, hey receiver, I applied a compression number 5. Okay, so the receiver has the same table. So whenever it knows that the transmitter made of number 5, it will reverse it. Good? Clear the question?
The question was how the
that the receiver, how the receiver will know what to do here, what has been applied, because this one has to be the reversal for this one. Here, this one is the reversal. How it will know what happened to make it its reversal? The transmitter should say to the receiver, I applied a compression number 17. No, 16 I said. 11, 5, 2. I didn't apply. When the receiver, the transmitter will say, I didn't apply.
Not equal probable?
Whenever they are equal probable. So if they are equal probable, there is no need for this one. So I did nothing. They came equal probable. Good?
That's for old, you said.
Yes, I said old. Okay, what is the problem with this one? With this approach?
More data.
What?
More data.
No. What is the problem with this? Do you like the approach?
There is more variations.
Very good. Is it suitable, the approach?
No.
Why no?
Why we need 16?
Sorry?
Why we need 16 of them?
Hey, how much you want?
Okay, you said there's more, right?
Sorry?
There's only 16 or there's more as well?
I said that in old system, old phones, they were 16. Now I will explain you what happens now.
Yes, there's less.
But before that, before telling I need you to know what is the problem so that why they made the change or the update. Sorry? No.
Incompatible.
No.
Not synchronized.
They have to be synchronized.
More variation of the
Yes, we here in the previous system they said, okay, let's make 16. Okay, maybe one of them is not 100% fit. They will approximate it. Okay, So here we will have some small loss because of the reversal. How to decrease this loss? This is y16. Make them 32 or make them 128. So whatever is the distribution here that is not equal probable, it will find a better match. No? Clear this idea?
Yes.
What's not clear, Salah? Okay, I will repeat. Here I have this distribution, right? Distribution A. Here I have another distribution. Distribution B. Both of them, they are exponential. This is exponential decaying, or this is exponential decaying. What's the difference between them? This is faster, decreasing much faster, right? So whenever if I have, imagine that I have a table of only 4. I have a table of 4 inputs, 1, 2, 3, 4. What I will put, in the first one I will put uniform, in the second one Gaussian, and the third one exponentially increasing, and in the third one exponentially decreasing. So I will put, what I said, uniform, so this is 1, this is 2, this is exponentially increasing, 3, or this is 4. If I have a table of 4, good? So in this table of 4, this one, where will it will fit? It's also exponentially decreasing, so it will fit here, but this is not the same. So they said, okay, if they are not the same, then we need a bit larger table, make it 8. So exponentially decreasing by how much? By which, how much slope? Okay, so this is 4, this is 5, or the same for the increasing. This is like this is 6, and so on. Good. The larger the table that you will have, you will make a better description of the distribution. Clear? Clear to all?
Yes.
Sure. So here, before they started with 16, now they made it 128. Okay, so increasing this table size will decrease the loss. Question.
What are we exactly sending? Are we just sending the shape of the...
No, we are sending the number.
So why don't we just send the exact opposite of the signal?
Because if you want to send the signal itself, this is the signal, right? How you will send the signal? You need to sample, quantize, encode. So you're telling another signal again.
This table in the compressor, yeah?
This table, it has to be at the transmitter or receiver. So the transmitter will say, I used compressor number 5. The receiver will say, this guy, he told me that he received number 5, so I will make the reversal for number 5. And the system will work. Clear now? Salah?
Yeah.
Saleh, Manu. Good, Saleh? Hamad? No, Khalid. أحسن. عبد الغني. Lost? Bored? Questions? Sure? All clear? Anyone wants me to repeat? No? Good. So this is the PCM with non-IID. Let's see other option, and before the other option, we need, as always, to motivate. Delta modulation. By the way, the word modulation is tricky, it's not correct. Okay, but whenever they came up with this idea, long time ago, they call it modulation. Okay, it kept modulation. Okay, so it might confuse the students because later we will see a whole chapter about modulation, but it is not completely different. Good. So what is this delta modulation? This properties first of all, then I will describe. This is the easiest approach. It will also work for non-IID. What else? Only 1 bit for encoding and for quantization. It sounds magic. Let's write down and I will explain how it works. Delta modulation, easiest, non-IID, only 1 bit for encoding and the quantization.
PCM just quantizes and encodes all in one device?
Sorry?
PCM, what does it do exactly?
It quantizes and encodes. That's what was the question. This one will also quantize and encode. Okay? But how it does that, the encoding? So here it is 1 bit. So this bit can be 1 or 0. Whenever 1, it means increase. Whenever 0, it means decrease. What does that? So here I have the function. Sometimes I can write it continuous for easiness, but yeah, we know that we are in a digital world, right? So imagine this is the function that we want to transmit. If you do a PCM, you have to check what is the value. This is 0.1, 1.5, 2.7, and so on. Whatever we have learned, okay? You have to do the whole procedure. Good? And you send each one of them separately. But now here with the delta modulation, they said, okay, we have an easier approach. What is that easier approach? Just tell me if it is increasing or decreasing. So I will give you the first one. I will initialize the system, and after that, just tell me increase. So here you will send the 1. Increase 1. Increase 1. Decrease 0. Increase 1. Decrease 0. Decrease 0. So the sequence will be 1, 1, 1, 0, 1, 0, 0. Based on that, I will know as a receiver what is the value. Do you like it?
Is it inefficient?
Inefficient? Why?
Because 1 bit at a time.
What? Because of? I didn't tell you.
Because it's 1 bit at a time.
This is perfect. And it is you are using only 1 bit. With PCM, maybe we need 7 bits, 10 bits. Okay, this one, only 1. 1 bit. So here, this is the cheapest. This is what I said, the easiest. So if you would like to buy a data rate from Ooredoo to transmit this one, you only need to buy 1 bit per second, per millisecond, per whatever here. Only 1 bit. With the other one, you need 7, 10, 12, whatever is the one. So here, this is the easiest. This is the cheapest. Cheapest in terms of the required data rate. So in terms of efficiency, very efficient. But it has problems. Like, a question or...
It increases and decreases by a fixed value.
But, good. So here, this one, the delta modulation, it increases and decreases by a fixed value. Here, increase by a fixed value. Decrease by a fixed value. Sometimes this is okay. Sometimes this is not okay. Examples. Good, stop before example. Anyone lost? Anyone want me to repeat? No? Sure? Fakhra? All good? Hamza? Hamza? Sure? Okay, good. Fixed value. Is it a practical system that we have always a fixed value to increase and decrease?
No. Maybe.
Okay, good. I like the main. Examples.
Let's say I'm dimming the lights. I just want to increase. It doesn't necessarily have to be something. Yeah, it can be fixed. I just want to increase شوي.
Okay, good. Okay, good. No, I don't like it.
If I use it as a switch on off.
On off switch, but here we have that value, so it's not on off on.
So,
Like,
I have your equal probability, right? Or something. Like if I have important things I want to focus on.
I need an example.
Like we said that the camera, for example, moving things.
Very good example.
Sound.
What?
Sound علي أو.
بس بتعلي بس هي بتطلع بتعليش كتير.
علي هون حط زيادة.
Bad example. What? أحسن.
Stocks.
What? What you said? No, don't be afraid. What you said? خلاص, I would like your example. What you said?
Stock market.
Stocks. يعني this is the worst example. The stocks, they don't increase or decrease. Okay, good. Example, for example. We said last time about the heat sensor, right? So the heat sensor, now imagine it is 25. After 1 second, it will be 25, 26, 24, but it will not be 30. Okay, so we will use it. So here, if you say, I will make the jumps in terms of 1 degree, so it could be 26, 25, 26, 27, 28, 27. So the increase or decrease is by 1 degree, and it is sequential. Good? For this system, this is perfect. Good? For other systems, like stock market, okay? So in the stock market, the value can increase gradually, but also it can increase rocket-wise. Okay? So definitely this will not work. Clear? Clear the 2 examples? Sure? Have lost? Sure? You follow us? Okay, good. Good, this one. So here, this technique, it has its properties, and you, as an engineer, you have to decide, can I use it or not? Depending on what is your scenario, you check if the increase is gradual, not gradual, it is fixed amount, the one that increases and decreases or not. Good? Abdullah.
Awaida.
Awaida. Good? You follow us? Yes.
So that modulation is good for slow or gradual changes, right?
For slow or gradual changes with the fixed interval. So here, it increases by 1 or decreases by 1 degree. There are 2 Hamza, right? Where is the other one? Meen Hamad? Hamad? Not here? Usama not here, right? Good. Done? Yes. Can you continue? Yes. Another disadvantage for this scheme, based on whatever we have seen, if you'd like to write the disadvantages. If we have a system that its increase is much faster, and here our steps are like this, only by 1, then they will not match. The other here, disadvantage 1, here, disadvantage 1. Disadvantage 2 is whenever we have a system that is fixed. That's it. So here, imagine this is fixed at how much you want to say. Yeah, good. This is the example, 25.5. The temperature is 25.5. What the system will do? 0. It will become crazy. So here, imagine it is at 25, then it will say increase 26. Decrease 25. Increase, decrease, increase, decrease, and so on. So here, we will say that the system went into a ping-pong effect. Okay? It cannot fix itself.
Doctor, the interval, instead of making it 1, can you make it 0.5?
Yeah, okay, good. So here, this system, it has to be predefined interval. Let me write it. I said it before, but yeah, it's good to write it here. So, predefined interval. For example, there is the temperature sensor. So, what is the temperature sensor here? By the way, the AC is not working.
It is.
It is working? It is working. It's not working.
I'm saying,
اليوم الجو بس جيد.
I don't know what to do with it. Always opposite. Okay, good. Fine. There is a temperature sensor here, right? So this temperature sensor, whenever they put the temperature, imagine this is the temperature sensor. It is not. Okay, but yeah, whenever they will install it, okay, they will put that temperature sensor. They will measure the first value. This is what we call initialization, because the system needs to increase, decrease, but yeah, it needs a first value. So they will initialize maybe it is sent by PCM, so they send the first value, then they will make it, okay, they predefine the value to be 1, and they will keep it running for years. Okay? And for years, you have to do this, increase, decrease, and so on. Good? So the interval is not variable, as your colleague said, so it cannot be fixed. Okay? And definitely we need initialization. We don't know the first value.
So what's the problem for the first graph? Disadvantage one.
Disadvantage one in case our system is going much faster in the increase. Okay? And only we can increase one by one, so we will be far away from the original one. Yes.
بس predefined interval ضيعت فيها.
Predefined interval, good. So your colleague asked, here you said that it is 1 degree at a time. So 1 degree, 1 degree, 1 degree. Can't we make it 0.5? We can, okay, but it has to be predefined. What does it mean predefined? So whenever I install that, I will put it, okay, and I will say what is the first value, and I will say it will increase and decrease by 1. Because it's only 1 bit. How can I do it? How can I change it? I have to go manually and change it. Okay, so this is why we say it is predefined. So the predefined here is 1. So it is 1 all the time, or 0.5 all the time, but we have to define it. This is why we call it predefined.
Explain the second graph again.
Second graph, and disadvantage 2.
Yes.
Imagine your temperature is 25.5. Good? You are here at 25. So the system will tell you it has increased, right? 26. But then it is still 25.5. So the system, after some time, it will, no, it decreased. 25. No, it increased. It has not increased, it has not decreased. It is the same value. But the system will be jumping, ping pong. Okay? Because it will think that increase, but it increased more than what? It decreased. Increase, decrease, and so on.
So how to solve?
Unsolvable. This is a disadvantage. We can do nothing. Good? Can I? So in terms, this is a new one, differential PCM. I want to compare PCM with delta modulation, and then I will motivate this one. So in terms of the number of required bits, who is better, delta modulation or the PCM? Delta modulation is much better. So here, delta modulation, it has less required bits than the PCM. So delta modulation is the good one. Okay. In terms of accuracy, who is more accurate, PCM or delta modulation? PCM is more accurate than delta modulation, but here we need more accuracy. So delta modulation is better in terms of the required number of bits. It's only 1 bit. Okay? While in terms of the accuracy, PCM is much better, right? Then they said, can't we have something to balance between the two? And not the best in terms of required bit, not the best in terms of accuracy. Is there anything intermediate? Then it becomes this differential PCM. So now with a differential PCM, it will be, we call it a trade-off. So here, this differential PCM is a trade-off, so, or a balance. What do you mean balance? So it is not the best in terms of required bits. So here it will be, we will see delta modulation, then differential PCM, then PCM. And in terms of accuracy, also, it is not the best. So for some applications, maybe this is the most suitable case. Something intermediate. Okay? Not the best in terms of required bits, not the best in terms of accuracy. Something in between. Okay? Serving both of them. Good? Motivation clear? Why we need this one? Then based on the three, what is the best technique to be used? غلط. You have to check what is the application. I'm tired from repeating the same story. Okay, so always you have to check what is the requirement for your application, what is needed in terms of the accuracy. Let me put examples. So the PCM, maybe in terms of accuracy is 95%. The delta modulation in terms of accuracy is maybe 65%. And maybe this one is 80%. In terms of the number of required bits, delta modulation is only 1 bit. This may be 12 bits. Then maybe this is 6 or 5 bits. Good. So you have to go to your application. What is the requirement? What are the constraints? Anyone here started the SDP project? So on the SDP project, the first thing that they will ask you in SDP 1, what are the requirements and what are the constraints for your design? Good. What does that mean? You have to check, because every requirement and constraint will end up with a different design. Okay? And you should be aware why you decided to do this design, why you decided for that design. This will be always the first question in the SDP. Okay? Why you selected this design? Maybe it's a good design and so on, but why you selected? What forced you to select it? So you have to say, okay, because you have a constraint of blah, blah, blah. But what does that translate in a practical life? In the practical life, the constraints, they come before. So your manager will tell you, we need to increase the performance of the accuracy. So say, to how much? Well, 80% is enough. Well, we have to go for 95. Well, we have to go for 99. Good? We cannot pay a lot in terms of the data rate. We have a wire, okay, that has been already implemented on the street, and that wire can carry only 1 bit. Cannot carry 12 bits. Or maybe we can improve it, can carry 6 bits. Good? So always you have to check what is the requirement, what is the constraint for your design. Cool? Clear? Hamza. This PCM I have not explained it yet, but I'm just motivating the why we need it. Now I will explain it. This PCM is this differential PCM. Good so far? Any issue with the motivation? Can we start? So how the system works? Imagine that I have these values, different samples here, 11.4, 9.7, 8.2, how much? 8.9, 10.7, whatever. Values. Good? If I want to do PCM, what I will do, I will encode this one alone, this one alone, this one alone, alone, right? Now, if I want to do it delta modulation, what I will do? This one lower, higher. By how much lower, I don't know. By how much higher, I don't know. Only lower and higher. It will work here, the lower and higher?
Yes.
It will work, but I will not be sure how much is the value. What is the interval? It is not the same interval. So here it will not work. It will give a bad performance. Good? Clear? Why delta modulation will not work? So here they said, okay, can we have some intermediate? How to do this intermediate? Can we check how much is the increase and decrease? So here, from 11.4 to how much I wrote? 9.7. How much here is the increase? 3, so this is 1.7. Good. From the 9.7 to the 8.2, this is 1.5. From the 8.2 to the 9.8, this is 0.7. From the 9.8 to 10.7, this is how much? 1.8. And so on. So the changes here. You see the changes? The range for the changes is between 0 and 2 maybe. While here the values are between, I don't know, 0 and 11.4 or 8.2 and 11.4. So if we encode the difference, so I will send the first one 11.4 and then with an increase or decrease of 1.7, increase or decrease of 1.5, so the number of required bits will be less. Why?
Because it's only telling the difference.
The range is smaller. So here the range for this one, here the range whenever we will deal with one is very large, the range, so they can change a lot. But here, whenever the range between them, we are encoding smaller values. And what we said today about the range?
To increase the range, will increase the
So whenever it is smaller, our range, our performance is better. Okay, so here, we said that whenever, so here with this one, we will have less range. And whenever we have less range, we have better performance. SQ and R, here better performance. And this better performance can be translated into something else. Well, I improve the SQ and R from 8 dB to 10 dB. Yes, I improved. But I only need it to be 8 dB. This 2 dB, can I take benefit from them in something else? Yes. How? Let me repeat. Good. So first of all, this scheme, okay, because now we concentrate on the difference. This is why came the word differential. So the differential is between, this is the difference between sample to the next. So now here the range is smaller. If it is smaller, then our range here is smaller, then the performance is larger, SQ and R. So if we follow this approach, we improve the SQ and R from 8 dB to 10 dB. Good? Clear so far? Done. Whenever you have it at 10 dB because of this, but you need it only at 8 dB, what you will do? You already decrease the range. For the SQ and R, what are the other parameters that they were in play? Bits. So here, you have, this is your improvement. But this improvement, you can invest it into less bits or less transmit power. Good? So here, this is the way. In the SQ and R, we have 3 parameters. They were the B, with the range, with the power. Right? Signal power. Signal power, or range, or B. So here, if you have increased the SQ and R, but you are still interested in the 8 dB, this increase or this improvement in the SQ and R, you can put it in terms of the bits, so you will need less number of bits, or you will need less amount of transmit power. Good? The idea clear? When this differential PCM will be useless?
When the difference is more.
Whenever these samples, they become crazy. Like what? What is the example? 11.4, 2.5, 9.7, 0.1, 11.7. So the jump is continuous. Okay? But whenever the jump is somehow close to each other, most probably this is doing very well. If it is like this, what is the only solution? PCM. Here the differential PCM, maybe it's even worse than PCM. So here it will be PCM. Awesome.
What happens when one of the samples is like that one, but the others are like near to each other?
You have to check. Okay, so it is better to use this one, better to use the other one. So there is no, let's say, no value. Say, well, if they are close enough, so how much is close enough? You have to check, and based on that you will.
No, but only one of them. Like one is from.
Yeah, so here like this, and then here 52.
Yeah.
Differential PCM will not work fine here. Okay, so is it suitable to neglect this one and it is an error and continue? I don't know. Good so far? Hussein, what's lost?
Less bits and
Where is less bits?
up, down, below SQNR.
So the SQNR depends on the bits, on the range, and on the power. So if I improve here the range, this improvement, okay, I will pay it to be better in terms of B or better in terms of the power.
Or less bits or less transmit power, right?
Good so far? About that, yes, sir. Still, we have 1 minute. Questions? Muhammad Noor? Sure? Yeah.
Application where it doesn't work is if the signal is changing radically.
That's it. So if the signal is changing suddenly, okay, like this will not work.
Does it work for only smaller ranges or like?
Okay, yeah. In theory, it works for small ranges, but how much small?
Depends.
This one you have to check, okay, and to see it is working better or not. Ubaida, all good? Sure? No? Nothing? So we stop here and we continue on Monday, inshallah.